Hi everyone, in this lecture we're going to be discussing von Gierke disease.
Von Gierke disease, also called glycogen storage disease type 1, is one of the inherited metabolic disorders of glycogen metabolism in the liver. There are 4 subtypes, but the 2 most common and well understood are type 1A and type 1B, which will be discussed in further detail.
GSD1 typically begins to present symptoms at around 3 to 4 months of age. Infants experience lactic acidosis, hyperuricemia, hyperlipidemia, and hypoglycemia, which will be discussed later in the presentation. As these children grow older, they are short in stature, have thin arms and legs, and a protruding abdomen as a result of an enlarged liver. In adolescence and adulthood, people with GSD1 have an increased risk of delayed puberty and a number of health issues, such as gout and kidney disease. But why do these symptoms occur? What has gone wrong during glycogen metabolism to cause these conditions? Let's break it down. Von Gierke disease affects the metabolic pathway of glycogenolysis, a catabolic process in the liver in which glycogen is broken down into glucose through the action of glycogen phosphorylase, the debranching enzyme, phosphoglucomutase, and glucose 6-phosphatase. This pathway is complementary to glycogenesis, an anabolic process in which glucose is used to synthesize glycogen through the action of UDP glucose pyrophosphorylase, glycogen synthase, and the branching enzyme. Let's review the process of glycogenolysis in more detail and see what goes wrong in von Gierke disease. In the first step, located in the cytosol, glycogen phosphorylase removes glucose residues from glycogen's non-reducing end, leaving them as glucose 1-phosphates until it reaches 4 residues from an alpha-1,6 branch point. The branching enzyme transfers a block of 3 residues to the non-reducing end and cleaves the remaining glucose. In the second step, also in the cytosol, phosphoglucomutase isomerizes glucose 1-phosphate to glucose 6-phosphate.
G6P can now enter glycolysis in a muscle cell, or it can be dephosphorylated by glucose 6-phosphatase in a liver cell to give us glucose. Let's take a closer look at this reaction. Under healthy conditions, glucose 6-phosphate would be translocated to the endoplasmic reticulum from the cytosol of a liver cell via a transport protein. Here, G6P would then undergo hydrolysis by membrane-bound glucose 6-phosphatase to produce glucose in an inorganic phosphate group. The active center of the glucose 6-phosphatase enzyme is comprised of lysine, 2 variations of histidine, and 2 variations of arginine. During this reaction, a phosphate enzyme intermediate is formed by the phosphorylation of a histidine residue as it accepts the phosphate group from glucose 6-phosphate. Freed glucose can now enter the bloodstream to provide much-needed energy to the brain or muscles. When a patient has von Gierke disease, this process can't occur properly. As mentioned, the most common subtypes of GSD1 are type 1A and type 1B. Type 1A is the most common form of this metabolic disorder, representing roughly 80% of cases. This subtype is caused by a defect in the G6P gene, which codes for glucose 6-phosphatase, leading to a deficiency of this important enzyme and preventing glucose from being freed from glucose 6-phosphate to enter blood circulation. Comparatively, type 1B results from a deficiency in the G6P transporter, which prevents the transporter from efficiently translocating glucose 6-phosphate from the cytosol of the cell into the lumen in order to be dephosphorylated. Both type 1A and type 1B result in similar disruptions to physiological pathways, which will be further discussed. The reaction for the hydrolysis of glucose 6-phosphate into glucose in an inorganic phosphate group has a delta G naught prime of negative 13.8 kilojoules per mole. To find delta G, we plug these values into this equation to get a delta G value of negative 3.23 kilojoules per mole, which is slightly exergonic.
When we divide the kcat value for glucose 6-phosphatase, 7 times 10 to the power of 2, by its km value for glucose 6-phosphate, 1.2 moles per liter, we get a kcat over km value of 5.8 times 10 to the power of 2. Please note these values were obtained for Norwegian rats and differ from values found in humans.
Glycogen metabolism in the liver is primarily affected in von Gierke disease because the enzyme glucose 6-phosphatase is deficient. Blood glucose regulates liver glycogen metabolism, but since the body cannot process glycogen into glucose, glucose homeostasis is disrupted and as a result, buildup of glycogen occurs. The increased concentration of glucose 6-phosphate in the liver stimulates alternative metabolic pathways and leads to hypoglycemia, lactic acidosis, hyperlipidemia, and hyperuricemia. Hypoglycemia is a condition characterized by low blood glucose. This metabolic state causes the constant stimulation of glycogenolysis and gluconeogenesis to increase blood glucose. Instead, liver metabolism of glucose is pushed into glycolysis to form lactate due to the absence of glucose 6-phosphatase. Compared to the normal rise in blood glucose in response to glucagon following the postprandial phase, those with von Gierke disease see a rise in lactate and no change in glucose. The absence of glucose 6-phosphatase commits the glucose 6-phosphate to glycolysis, resulting in the increase of lactate production. Therefore, instead of using glucose, the brain uses lactate as fuel during prolonged periods of hypoglycemia. However, constant and elevated lactate levels lead to metabolic lactic acidosis. With an increased concentration of pyruvate formed from glycolysis, synthesis of acetyl-CoA occurs, which is the starting metabolite for lipogenesis. Thus, excess production of triglycerides and fatty acids occurs. This increased storage of fat, in addition to the accumulation of glycogen in the liver, leads to hepatomegaly. It also causes the characteristic dull face seen in infants suffering from von Gierke disease. With an excess amount of glucose 6-phosphate, it is used in the pentose phosphate pathway to produce ribose 5-phosphate. This production of ribose 5-phosphate ultimately creates a buildup of uric acid, leading to hyperuricemia. Additionally, decreased phosphate concentration stimulates adenosine degradation, which results in an increase in uric acid formation as well. Finally, lactate competes with uric acid for renal excretion, which also contributes to hyperuricemia.
So now let's get into the mutations causing GSD1A. So the cause of GSD1A is a mutation on chromosome 17, which encodes for the G6PC gene. And this gene is responsible for producing the catalytic domain of G6Pase. Most forms of the mutation cause the gene to become inactivated and therefore can no longer produce G6Pase, which creates an imbalance in glucose homeostasis. The most common mutations of GSD1A are R83C and Q347X. Both these mutations are a result of point mutations in which there is a single amino acid substitution. As stated on the previous slide, the R83C mutation is one of the most common mutations, and it is caused by an amino acid substitution. The activation center of G6PC is comprised of 5 amino acids at various codons, one of them being arginine 83. The R83C mutation occurs in exon 2, and it is responsible for converting the arginine at codon 83 to a cysteine, and in turn altering the activation center of the G6Pase. The other common mutation is Q347X, which occurs on exon 5 and is caused when the 11 amino acids at the carboxyl terminus, located in the cellular cytoplasm, are truncated. This results in the inactivation of the enzyme G6Pase, similar to the R83C mutation.
The social aspect I will be discussing is von Gierke's disease present in Ashkenazi Jews. This population originates from Rhine River in western Germany and northern France. There has been multiple studies on this population regarding von Gierke disease, every time with similar results. As discussed earlier, the R83C mutation is the most common and is also the most common in this population, although the Q347X mutation is sometimes found with the R83C mutation, but this is only 6% of the time. In the general population, von Gierke's disease is present in 1 in every 100,000 people. In the Ashkenazi Jewish population, it is present in 1 in every 20,000 individuals, so their chances of having the disease is 5 times greater. Many people are also carriers of the disease. In the Ashkenazi Jewish population, 1 in every 71 individuals are carriers, which contributes to their increased risk of having the disease. I will also be discussing treatment methods. The biggest part of treatment is diet. Individuals with this disease should try to keep normal blood glucose levels, so meals should be low in sugar to prevent glycogen buildup. One of the best foods for treatment is uncooked cornstarch. This is because it slowly releases glucose at a rate that it will not build up at. Forms of sugar that are not glucose, like lactose, sucrose, and fructose, should be avoided to prevent other pathways from contributing to glycogen buildup. Multivitamins and supplements are often recommended due to the restriction of foods that can be consumed. There are often pharmaceutical treatments for its symptoms. This includes HMG-CoA mutase inhibitors to treat lipidemia as they reduce cholesterol levels. Allopurinol decreases the level of uric acid to treat hyperuricemia. In more extreme cases, dialysis may have to be done or a liver transplant. Thank you so much for watching our presentation. Now we have time for questions.